Now on to our talk today. We have Scott Napier, who's Global Director of Consulting for Mira Geoscience. Scott's a geophysicist with expertise in geophysical inversion and extensive experience with borehole, ground, marine, and airborne EM interpretation and processing. He's worked in Canada and internationally on oil and gas, uranium, and base metal exploration teams with a proven track record of discovery. Today, he'll be discussing the utility of SimPEG to improve 3D EM inversion models. He'll provide examples using ground EM data from the Iberian Pyrite Belt to discuss the data processing, inversion workflow implemented using geoscience analysts. We're really happy to have you here today, Scott, so thanks for coming. Over to you.
Thanks a lot. Thank you. Yeah, so I'm going to be talking about 3D time domain inversion with open source SimPEG. And this is really a case study for the applications of this in the Iberian, for VMS exploration in the Iberian Pyrite Belt. So, okay. So this is the introduction and setting here. The study area is in the Iberian Pyrite Belt, IPB, on the Portuguese side. And we're located near Aljustrel mine and Neves Corvo mine. These are both supergiant VMS deposits, greater than 200 million tons, both active copper zinc mines at the moment. The target here is a similar deposit, late Devonian age in the BSC volcano-sedimentary complex lithology. You can see the stratigraphy here. So you have this tertiary cover. It's very thin skim just on the northern edge. Not really important. Above that, you have the Myrtilla formation. This is a fleesh sequence, turbidite sequence of shales and siltstones. You have the VSC, which is minor amounts of volcanics really, but mostly purple and green shales and black shales as well. And then below that, you have the PQ, phyllites and quartzites. That's also really just shales. So it's shales all the way down. Shale. It's conductive rocks. Background conductivity is between 100 and 200 ohm meters, somewhere around there. They have, other than the purple and green shells that tell you that you're in BSC lithology, it's pretty difficult to tell where you are. They need paleontological dating to really know where you are in the time sequence of this, because it's just a whole bunch of shales, different colors. The setting here is PQ rocks that have been overthrust on top of VSC. And then you have later deformation that's made this anticline in the VSC and an erosional surface that's cut through that. So that's why you see this, VSC sitting within a background of the basement rocks, which is kind of unusual for Silica. Then late north-south oriented normal faults cut through the geology here, but not super significant in terms of displacement. So the study area is covered by this deep search ground EM survey. This is a survey that was put together really by Dennis and Dick West at Lundin at the time. So it's using a squid receiver operating at 5 hertz. You have these 1,000-meter, 1 kilometer square loops contiguous, so you don't have to pick up as much wire. You can share the sides of the wire. 100-meter station spacing and variable line spacing. So the survey was designed to detect one of these massive VMS deposits. So often you would survey a single line through a loop. If you didn't see a favorable response, you can pick up, move on, cover a lot of ground. And this survey was operating at the time, about 15 years ago, for several years, and a huge amount of this data was collected in the Pyrite Belt at that time. So before I get more into the data, I just want to give a little bit of background about what's different about the Iberian type of volcano-sedimentary, emphasis on sedimentary, massive sulfide deposits. So that's the title of a paper by this fellow Saez and co-authors. This is a figure of his that shows the deposit formation. So really what you're looking at is well, first of all, IPB deposits are unique in terms of their size. So you're looking at a belt that's full of multiple over 200 million ton VMS deposits. You've got really massive deposits like Neves Corvo and Rio Tinto. I've heard Pre-erosion might have been the largest accumulation of sulfides on the planet. So over 1 billion tons of sulfides there. So what makes them different? Well, this is a sort of schematic by SAS and showing sort of mineralizing fluid control is controlled by this normal fault. So you have a Horston graben setup. The mineralization is being emplaced mostly on the graben side here and a little bit on the horse side. So this is exactly what you see at the sort of the largest ore body at Neves Corvo, the Lombador. You see this exact situation, but it's not to scale. So on the graben side, the mineralization extends about 1 kilometer out from the horse block. And then on the horse side, it's only 15 to 25 meters. It's very thin up there. So 100 meters thick, it extends hugely out into these basins. At the same time, you have this deposition of the massive sulfides. You've got, this is a quiet ocean basin. You've got deposition of these black shales, organic material falling into this. So the massive sulfide exists within a horizon of black shales. So these deposits he characterizes as felsic, siliciclastic VMSs. Certainly there's aspects of that, but they're on a spectrum somewhere sitting between a sediment-hosted massive sulfide, SEDEX deposit. So, and that explains their size and the stratigraphic control that we see in these deposits. So there's a black shale association with these deposits in the belt. So many of these deposits are associated with black shales, Neves Corvo, Tharsis, Sotiel, as now Coyar. And this is another figure after size, just showing massive sulfides are the dark material, and the horizontal stripe lines are black shales. And so 4 out of the 6 deposit examples that he has in sort of the schematic are all sitting right within the black shale. So it holds true for many of these deposits. So the question is, how can we use these stratigraphic conductors to better target our exploration drilling? We propose that in this setting, VMS ore bodies maybe appear as conductive bright spots within a stratigraphic marker horizon of otherwise moderate conductivity. So they're potential marker horizons. They tell us where these prospective basins are, and they may help us guide us into these areas. So we shouldn't be running from these stratigraphic conductors. We should be running towards them and trying to characterize them, trying to look within these stratigraphic conductors. So how can we improve the modeling of EM data related to these features? So let's get back to the data. So this is the data from that grid. It was one of the grids that had the best responses of all the EM grids that we collected in the Pyrite Belt during those days. Certainly stood out as something interesting, and we looked at it for quite some time. This is the profile. You can see this late time Z profile here. Seems to indicate a dipping conductor. If you look at the decay of one of the decays here in Z and fit a time constant to it, you got a time constant in the range of 12 to 16 milliseconds. It's not that high in the world of conductors, but for the Pyrite Belt, this is pretty significant. This is similar to, it's actually better than the decays that were measured over top of the Lombador ore body. The conductance that you expect from a Pyrite Belt deposit is somewhere in the range of 300 to 500 Siemens in that area. So this pyrite, dominated by pyrite, pyrite's conductive, but it's not really all that conductive. It's not like pyrrhotite. It's not. So when we looked at this, I did some plate modeling at the time. I did the plate modeling in free space, but also with Leroy, so with the background half space. Kind of inconclusive. You just really end up with these giant plates, fairly low conductance. Depending on how big you make the plates, you can get different conductances out of them. But there was never really a discrete target that said, we could differentiate this from a stratigraphic black shale horizon. This would be the target. We also did 1D inversion. That was really the go-to interpretation mode, given the success that it had at Neves Corvo. It really defined the ore body quite well there. It was bang on, really. But in the 1D inversion here, you just saw sort of two parallel northeast dipping horizons about 30 degrees. I'll show you that later. But there's no bright spot within those horizons from the 1D inversion. There's nothing to target. The question remained here, what's the contribution of the conductive background? Is it all just barren black shales, or is there something significant here? And so the hope revisiting it now is that 3D inversion might be able to provide more insight. And that's where SimPEG comes in. So SimPEG, I'm sure many people here know, is an open source general library for geophysical modeling in Python. At the time, so this is a presentation that I originally gave. This is an update to a presentation I gave at KEGS in 2023. So at the time, presenting this in 2023, 3D time domain EM inversion was newly implemented. It's been worked on quite a bit by Dom and other people since then, and it's looking quite good now. It involves a octree mesh discretization of your model domain, the built-in tiling of the forward problem. There's a direct solver for the forward problem, which is highly accurate solutions, and explicitly storing the Jacobian sensitivity matrix in RAM or on ST hard disk. And that means fewer calls to that direct solver overall. And you can use that Jacobian sensitivity for a sensitivity-based weighting, and that avoids ring-shaped artifacts around your most sensitive cells, the ones that are near your transmitters and receivers. We're also using Geoscience Analyst's Pro Geophysics and the SimPEG Python interface. So there's a bunch of components to that. So there's an importer for a Mira format TEM data, so you can just quickly import your time domain EM data straight out of the file import. There's the ability to convert your data units. So SimPEG is expecting very specific and somewhat unusual units. So SI units, which nobody uses. So you can convert all your units fairly quickly with this data unit converter. You also need to be able to define your channel delay times once you've imported your data. So there's a dialog box for that, and you can load your channel delay time straight from a Maxwell channel file. You also have to select the delay times that you want to use in the inversion. We don't want, in this case, we're removing the first 8 channels. We don't want to deal with delay times that are sensitive to features that are smaller than our model cells and really not significant to our exploration objectives, right? We're not interested in the first 25 meters of the ground. This is a deep target. So we're going to remove those channels. They're just going to hurt us. For a time domain approach, we're going to need to discretize the current in the transmitter as a function of time. And I've got a little bit more about that, but there's a facility here to create that discretization, do it quickly by entering sort of standard values. So we'll talk about this on the next slide. There's octree grid designer, so you can construct octree meshes based on various parameters that you need for that, how quickly you expand your cells and all that. There's a dialog box for that. There's a SimPEG, the SimPEG Python interface, and all of the inversion settings and forward modeling settings for the various types of modeling that you want to do. And then there's submission of inversions to the cloud for fast remote computations. So it's sending this off to a remote server, in this case Azure, but it can be any kind of high performance computing that you want to use. There's inversion progress monitoring. There's a website, or you can just download this convergence curve, which really shows you the model objective and the data misfit reduction over time. And then under your high performance compute status, you can just hit the download button when you're done or when you're ready, and download your results into your Geoscience Analytics project. So just talking about waveform design, we need to discretize the current in the transmitter as a function of time. We're doing this in a time stepping way. It's not frequency to time. We're stepping through time. And so you can set up your theoretical parameters or your waveforms, so your turn off ramp and your pulse width, that sort of standard stuff. And then decide how to discretize your waveforms. So the spacing of your on time, the spacing of your ramp, and the spacing of the later part of your on time. So you need to use multiple different time steps. You're trying to discretize as few as possible time steps with as few as possible changes in the time step size. And so that's just what you're needing to think about. We want to make sure that our time steps here in yellow are that we have at least one time step for every time channel, the blue dots. So when you transition to that larger time step, make sure you have at least one time step crossing through that area. So when you have a result, this is the data fit. So this is the data fit on a log scale. We've got X above and Z below. There's only X and Z in the Landham squid. There's no Y component measured. And this is for all inverted channels. So between 0.42 milliseconds and 42.7 milliseconds. You can see in X, we're matching the observed migration of this X crossover with late time. Pretty good fit, I would say, between observed, the black, and the predicted red. So that's all the channels, just zooming into the last 7 channels here, the late time. On a linear scale now. Pretty good fit to the late time. You can see the noise here starting to develop in the late time, but you're getting a pretty robust response of the model to this data. So we're not getting hung up by trying to fit some of these, clearly what's noise, it's just running through there. So we're not overfitting the data in this case, I don't think. It's doing a pretty good job. So let's look at the results. So this is a section I'm going to show. Here on the map here. So there's a section A prime. This is the residual gravity. So you can see that there's a pretty nice looking semicircular or circular gravity anomaly. It sits right above this profile. It's interesting. There was a hole, we'll see this later, drilled in the 1980s on this gravity anomaly. And this is the result we got originally. So this is back, 2009, EM1DTM inversion of this data. So those are those two sort of bland looking, 30-degree dip horizons that ultimately led us to walk away from this area at the time. But this is the 3D inversion. It's done originally for my client. I did it with H3D, and then we followed up with inversion with SimPEG. So the H3D really pulls out an interesting anomaly here. And so does the SimPEG, although it looks quite, I would say different from H3D. At the time, I didn't realize, but SimPEG was only running Z component. Don had done this inversion. And so multi-component inversion has been added to SimPEG since 2023. And you can invert, X, Y, Z, no problem with SimPEG. And I'll show you some more updated results from SimPEG near the end of the presentation. But I think they're generally pulling out the same features. You're seeing this conductive discrete anomaly here on the section. So when I look at that section, I kind of think about a possible, it got me thinking about this link to the genetic model. So we know that the Pyrite Belt underwent very heavy compression after the deposition of these deposits. And in this late compression, you can have these normal faults be reactivated. So there are zones of deep-seated weakness in the crust. And under compression, these things will be the points which break. And often you find these pyrite belt deposits on anticlines. We've got Rio Tinto, Neves Corvo, Darcis, Massa Valverde. Those are just deposits that I've worked on. They're all sitting on anticlines. I'm sure there's many more in the belt. So I think the top of this thrusted ramp is a very prospective location for VMS deposits because it's broken at that point. They controlled the original deposition. So that area. And if you look at these results, I think you can make a case that it really does look like a textbook thrust ramp situation, and this bright spot is appearing right on the end of that thrust ramp in this case, and here as well. So further to that, I mentioned that 1980s drill hole. Here we're seeing a plan through the 3D inversion result, showing the location of the drill hole sort of right near the top of this conductor. And then you've got the drill hole trace on the section here. And so the borehole EM, there was a borehole EM survey in this old data. The data is lost to time, but it's a note in the log that says there's an awful response measured at 630 meters depth in the data. So that at that time in the 1980s, borehole EM systems were single component axial data, so you could know that there was an awful, but you couldn't know which direction it was coming from. And so that's the only information available.
Unless you did multiple loops.
Unless you did multiple loops. Yeah, I mean, the data's gone. It doesn't even say who collected it. Pardon me?
Where's, didn't we collect that?
Did you guys?
We didn't do it, no, we were there in the 90s. We were up there in the 80s. I forget one, because I did 3-4 bubbles.
Did you? Yeah.
Yeah, that was like 93.
93. Okay. Yeah.
Trying to think.
Anyways, it's lost to the miss of the data itself is gone, right? It's just a note in the drill hole log that says there's an awful at 630. Lithology at 630 is a volcanic. What's that?
It was awful.
I think. So the lithology at that depth is volcanic ash flow tuff. That's a good thing here, right? That's the right lithology to find this material. So this is where the KEGS 2023 presentation ends. This is basically the last slide. Call it a day. So I got permission from my client to present the next few slides, which I think are interesting and maybe a cautionary tale. So here's this is summer 2023. They drilled this hole right into that conductive bright spot on the inversion result that I had there, that, you know, bright spot looking thrust ramp thing. So what was the result? Well, hold on just a second. This is a image out of the report that I gave my client after doing the inversion. So I didn't do just one inversion for them. And I've been just showing you one result all along because that's the result I liked. And it sort of fit in with that story. But there were three different inversions done. So the upper one here is no vertical to horizontal bias. It's just 1-to-1 unconstrained inversion. Basic. The second one is unconstrained, but with a very strong vertical bias. So just trying to find something quite vertical looking. Because that's, I mean, one idea that they threw out there was maybe things are quite vertical. They're not horizontal like we're seeing. And then the final one that I've been showing you all along was constrained by the 1D inversion. So the 1D inversion was the reference and starting model for this inversion. So in this case, and that's what I've been showing you all along. I wrote this in the report based on the visual appeal of the models. I believe that the 1D constrained inversion is the best of the three provided.
Those are all SimPEG.
These are all H3D. This was the original work done prior to SimPEG. And so I'm showing you H3D results here because I had all three.
Sorry, and the H3D used the ZNX component?
Yeah. Yeah. And so, and I think the X is really critical. It's this kind of target. Yeah. It would have been nice to have Y too, actually, but we're at Milan times grid. But and all of these fit the data more the same, right? These are all valid models. They all do an excellent job of fitting the observed data. So what was the result? This hole was drilled. The result was entirely negative in terms of mineralization. There's pyrite down there. I mean, but there's pyrite everywhere. It's a pyrite belt. It's, you know, it's not all that significant. But at the bottom of the hole, we're in the right rocks. Lower VSC, that's the expected position of the ore horizon if this were a Neves Corvo analog, which is the idea that they have in mind. This looks something like Neves Corvo. Interestingly, their home base at Aljustrel, the mineralization sits in the upper VSC and the lower VSC is completely missing. So there's different times where these deposits have existed or have been placed. But if it's like Neves Corvo, it's that time horizon, it's in the right spot. The hole was surveyed with borehole EM at 6.25 hertz. And this is what you're seeing, axial dip and strike direction. So last 5 channels, you can see that there's a very strong EM response per very broad off hole here. You can see it best in the cross hole because there's not so much background response. Lasts to the latest time. The data quality is marginal, could be better for the system, but you can see it. It's a pretty good conductor. And it's so that off hole sitting behind the hole and to the right, if you're looking down. So let's take a look at that plate. So I'm seeing that plate from a couple holes. I'm not showing the other hole that I can see it from here, but I can see it from more than one hole. I have a fairly good indication that plate dip is pretty steep. It's around 60 degrees. So, and that's what they're also seeing in their drilling, is that geology is indicating that dips are pretty steep. It looks like, you know, 60 degrees is the dip of the geology here. And so that 1D dip that we're seeing all along is just, it doesn't make sense. It might be just that kind of artifact that you get from 1D where it makes, you know, steep dipping things look like they have, you know, shallow dips. It might be also combined with the host response. My sort of reliance, and, you know, I've been looking at this thing in 1D for a long time. I think that biased my interpretation of this area. I shouldn't have been so heavily focused on the constrained by 1D result. If you look at the unbiased or the vertical biased, if you had targeted that with a drill hole, you would have hit this plate. You would have gone for a shallower dip and you probably would have hit this feature. So I think it's a bit of a cautionary tale. I think don't get so focused on one of the models. I think we could have, you know, planned a drill hole that could have, you know, intersected a conductor for all of these models. It would have been a bit shallower, a bit longer of a drill hole, but it would have been a safer approach. Anyways, yeah, I think other than that, I think 3D inversion is working very well to image this compact target, right? We've come a long way from those 2 shallow dipping 1D horizons. We've drilled a hole. We've confirmed there's, you know, significant conductor, 500 Siemens plate down there, 500 meters by 600 meters. It's a big, good conductor. I think it's confirmed that there's something significant there. We just need to really go and drill it. I think the other thing, Joel, is that 3D modeling is really recommended for this legacy data. I think in this environment, it's working really well. 1D is potentially very misleading. So summer 2024 drilling is planned here. Just the update to the SimPEG. So now we're running with X and Z in the updated SimPEG. Here's a comparison between the SimPEG with the vertical bias and the SimPEG and the H3D with the vertical bias, and very comparable results. I think we're seeing the same things in those same colors.
So the big difference is the earlier slide where you showed big differences between the H3D SimPEG. That's all because you only did one component.
I think so. Yeah, I think that's a big difference. Yeah, and I think the X was really critical. I think you're almost, if you had to have one component, I would rather have the X than the Z in
What's the
this setting.
difference between X is just a facial derivative, say.
I guess, but the Z is swamped by the background response.
By looking at,
Well, the X seems to be much less sensitive, and that migration of the X and then the inversion locking onto that migration of the X as it moves across.
but X is generally a lot noisier.
Yeah, I mean, is it noisier in a squid though?
Huh?
Is it noisier in a squid?
Well, I don't. I mean, there's always more orientation issues.
This is.
Yeah, I guess there's orientation
There's
issues. I mean,
orientation issues and your telluric fields are more noisy in the X.
right,
So generally speaking,
X is noisier.
noisier.
They're
I mean-
using compass.
Huh?
Yeah,
They're using compass.
yeah. I mean, I think having both is better, right?
I mean, you'd be better off doing tighter station space. Because then you can calculate. the direction.
Well, if you look back at the map here, I would like to have a lot more data than we have. Like, and I can't complain to anybody because it was me who did it, so it was. So,
So do you think you know, at one point you said you used the 1D as the starting and as the reference, right?
yeah,
And the risk there is that after every iteration, it says, how close am I to the reference? And it's always trying to drag you there.
yeah,
So have you run one where you just use it as a starting model to give it a kick in the ass and then let it run and.
on the basis of these results, I think to hell with that 1D model. I don't think it makes any sense at all. And you're better off without it. Yeah. But I don't think that's always the case. I mean, in Lombador, we're talking about Lombador, the 1D model worked great. Did a fantastic job. It's just so big and it's 40 degrees. Yeah,
Scott, it's the Wendy model, so one component.
it's only one component, yeah. And it doesn't really make sense to have the X into 1D for that. And I think maybe there's a more conductive background the 1D was picking up here. And that may have made the 1D less conductive.
It's a fair point, though. I mean, if the 1D was Z only, you're gonna get pancakes because the 3D model is pretty flat too, right? It kind of like everything is. You saw it earlier on. The SimPEG model was kind of it's also
Pretty
kind of
flat.
Yeah.
But that SimPEG model was run with 1D as starting a reference, right? Yeah. So those were apples to apples comparisons of starting a reference, whereas this one's on vertical bias but unconstrained in this case, which I've sort of gone to thinking that's a better approach. At least in this situation, and we have confirmation that the geology is steeper than 1D can handle. So I think that's the right thing to do. In this case, now SimPEG, like Dom, you've done a lot of work on SimPEG, making it fast and efficient. This case, 25 loops. The runtime is 24 to 36 hours to completion. So not bad. Pretty similar to what H3D was doing for the same data set. And I think in this case, for the entire data set, which is about 45 loops, I had to split it into 3 different tiles, run those separately, make sure they all fit to the same degree, and then merge the results back together to cover this whole area. And I think SimPEG would be capable of running the entire data set 45 loops in one inversion, and it does its own internal tiling loop by loop. Something that as a geophysicist you wouldn't have to deal with and would just make, save a lot of time for somebody who's doing this kind of work.
How many CPUs and how much memory and
Were you running on that 120 Ether? Yes, 120 CPUs and 450 gigabytes of memory.
We're not close to that though for memory consumption. Maybe
Memory's nowhere near.
like
Yeah,
10%. Yeah.
can't really. So 45 loops would be no problem.
If you ran it on that, the other 8, the 44, it should be 44 C, how much longer you can.
Thing goes that part, you still kind of saturate after a while, even if you throw more power at it. It's hard to tell. Yeah.
Yeah, I get the sense that 44 RC or ACR 44 RC would be pretty similar. I think.
Change the way we
So just the RAM,
do
I
things. Like,
mean, unless that big machine has got wafer RAM.
yeah, but again,
Yeah.
RAM is not really a limit. It's just it's the runtime.
What's your cost for it?
Spot price. It's like $1 a day or something.
It's cheap.
Yeah.
Yeah.
I lose it, but it's spot. You can't lose it, but if you do spot, it's very cheap.
Yeah. There's also another provider out there, Doug, is very, very cheap. We haven't tested these codes yet on Doug, have we? The time domain code,
I have.
I haven't
some
either.
yeah.
but they're cheaper even than spot instances of Azure. So yeah, we've demonstrated that efficient 3D inversion can be achieved using this open source inversion package SimPEG. We benchmarked that 3D inversion with existing 3D inversion, that H3D. I think very comparable results now using both components. I think a really key part of this is pro geophysics and geoscience analysts to make this 3D inversion part of your day-to-day toolbox. That's the data handling, inversion interface, and access to the cloud. And I think ground EM and the combination of ground EM and 3D inversion are working really well. Despite the issue there with missing on the first go, I think we'll get it next time. Stay tuned for the update. And it works really well. My finding is that 3D inversion works really well for this target conductive host, not too conductive of a target. The contrast seems to play a role there. I've had less success, should we say, in environments that are where the host is much more resistive. That's been my experience. So higher metamorphic grade, those sediments become pretty resistive pretty fast, and then you start, at that point, parametric models work a lot better. You can ignore the host response. It's insignificant, and really you're just looking at a reduction in a conductive volume. And in those settings, then plates are working fine. There's no reason not to. But here, where it gets tricky, where you have all these responses mixed together, I think this 3D inversion is working just as it should be. What are other areas of applications? Certainly in other VMS belts where that metamorphic grade isn't as high, the host is still pretty conductive. So Turkey comes to mind immediately. I'm sure there's others, maybe northern BC, where you've got those similar situations.
That's a basket.
Athabasca, I mean, the basement is really the basement metamorphic grade is really high, right? So the basement is generally resistive in these thin conductors. So parametric modeling in the basement works really well. And then if you're trying to characterize a sandstone, then yes, I think it would work really well. So I think Athabasca needs a hybrid approach. I think there's an application for this potentially in porphyry exploration in a certain type of environment. I think there's, in a place where resistivity is not working well, like high contact resistivities, you're having trouble getting signal into the ground, or and in places where maybe I think you can improve on the resolution that MT would get you in a setting like that. I think MT, you've got a plane wave coming in, it's just one source really. It's a very diffuse source. And this, large loop EM, you're illuminating conductors from different sides. I think you're getting more potential for resolution in that range, about 500 to 1500 meters. And that could be an important area to characterize well in terms of conductivity. So I think it's worth testing that in that kind of, Andean terrain, or Arizona, Mexico, that basin and range porphyry style area.
But you signing up to wire at a.
I'll
4,000 meters.
Well, let's test it in Arizona.
Based on this experience, the inversion, can you suggest some improvements in the actual field collection? We have to use that.
I would love to see.
Move the loops further apart.
I would love to see overlapping coverage from inside the loop, outside the loop. I think that improves your ability to resolve things. So
Overlapping loops is that
over like continuous loops like we have.
Yeah.
But our coverage in this survey was typically, although there was a few lines and those were right where this thing was, where we extended outside the loop 1 kilometer, inside the loop 1 kilometer, and then outside the other side. And we moved the loop and then we surveyed the same thing, like all the way through. And if you had continuous coverage like that, you would see everything from every different angle. And I think that would be, that's the stepwise loop, but also surveying inside the loop.
Yeah, that's chemicals.
That's Cameco's system, right? That's every possible.
This idea I stole.
When you said this,
Maintained it, that's.
Yeah.
That way. Hmm.
I think it's Howard. Chief physicist.
Did it. We did it when I was looking for one. Started.
but the stepwise loops I'm seeing in the Athabasca, they don't measure inside the loop; they just measure outside the loop.
No, it used to go right through.
You go right through the loop. Okay, yeah. But I think for this kind of target, going right through the loop would be inside, outside, both sides would be.
I did that in hospital, the technical part.
Oh yeah. Sounds like some 3D inversion.
Huh?
Recommended. Sorry?
I thought we collected one.
No, there's no Y on that instrument, but like turned it around.
Well, that's put a bit more noise on it.
Yeah. Yeah, that's it. That's all I have.
Talking, if you guys have questions or people online can type it or unmute yourself.
Do we have many online? No?
Yeah, 17.
Really?
I can show you.
Can you hear me? This is Nick.
Yeah, Nick, go for it.
Scott, did you do any synthetic modeling with really conductive half space or conductive layering and inserting anomalous bodies in that to convince yourself that you really can detect them at those depths?
No, I haven't. No. But I think the borehole EM result there proves that we have. At least in my mind.
Well, as you said, there's pyrite everywhere, and it's really conductive all throughout. So
Yeah, but you don't see a 500 Siemens awful like that everywhere. That's very unusual.
Okay.
Yeah. Yeah, the host, you see the host certainly, but you don't see it responding at those late times in that way anyways. That's a discrete conductor for certainly in the borehole.
Scott, about the comparison between this 3D or H3D and SimPEG. Is there a difference in the sensitivity weighting between the two codes that will also explain differences?
Yeah, for H3D, I just came up with a weighting, completely empirical. It's a distance-based weighting from sources and receivers. And 1 over distance scale and thresholded. Dom will have to tell us what the SimPEG is doing, and he's gone for weighting. But yeah, it's using the Jacobian. Dom, tell us what the SimPEG weighting is doing. It's a setting in the inversion set. It just takes care of it, which is nice.
Just the
Which is
sensitivity
great.
weights thresholded using Devon's amplitude cutoff. So like after 1% of the amplitude, you just level the.
Yeah, okay. Yeah, just I'm wondering if that was also a difference between the two inversion results.
It's mostly for the near surface because the 1% cutoff like ends up pretty shallow. So we're really killing the near electrons, and after this, it's more or less
That's kind of
Smoothing.
what my distance weighting looks like too.
Yeah.
So you're doing that just with like a half space world to compute the.
Oh, no,
you're updating it every.
Right, yeah, we have a sensitivity, we can calculate it explicitly.
Yeah,
So
yeah.
we just update it every time, yeah.
Whereas mine is fixed, right? It's never changing.
For
For H3D.
Cause that might, I mean, it would be interesting to try just doing sort of fixing the sensitivity weighting.
Yeah.
To start
Throw
and
it out
seeing
there.
if that makes a difference in the targets.
Absolutely.
I think in the end, these things are really pretty similar. I don't think the sensitivity weighting is having a lot of. This thing would be it, right?
Scott, because no one's asked, are you happy enough with that apparent offset between the plate and that conductor?
I don't have an
Is
explanation.
it within
for
the
it.
fudge factor?
I think
Model,
the
the cells, or you,
we're down at 650 meters, we're up on the surface.
So you're close enough?
I think the fact that we got close enough with that drill hole to see the offhole
Yeah.
is an exploration success.
Yeah.
And that's how these deposits get discovered, and that's, our discovery when I was there in Portugal was exactly the same story. We got close enough, we got an offhole. The next hole was 5 meters, and the hole after that is 50 meters.
what that distance looks like? 200 meters, right?
200 meters, yeah.
No, but you've read it, or you have.
Yeah.
I'd be happy with it, but I don't know if the geos would be working with it.
Well, I mean, they're not happy that this hole didn't, hit 100 meters of massive sulfides. There's disappointment.
But the unbiased was almost closer.
Yeah, no,
Yeah.
it's. I think if you targeted, like I said, if you targeted that, thinking it's steep, you would have drilled a shallower angle hole, and you would have passed right through this plate.
Maybe, put the edge.
Yeah,
Maybe you need to drill
yeah.
the center of it anyway. So.
Just gotta presume there's fair amount of uncertainty. Since the beginning, and so.
Yeah, I mean, the borehole EM has, there's quite a bit of uncertainty from the ground, and we're down pretty deep, I think, admittedly. How well can you resolve the dip of something at 650 meters? The borehole EM I'm seeing from a couple places, I'm much more certain of that dip that I'm seeing in that plate.
So if you look this back to the gravity, just essentially look at people.
Can't talk about the gravity, sorry. Yeah, no, but there's a nice gravity story there. That's for next time. That's the next.
Wavelength. Anyway, be interesting to see.
There's Z10 too. Z10's the. My colleague Stanislava. Hopefully, we'll one day be able to talk about the Z10 here.
So I'd be shocked if the gravity could see a small body at 650 meters depth.
Well, I don't think it's that small. I don't think
But they have even a plate.
the
That anomalies. Yeah,
that's bigger. That's not explained well by the plate, even if it's 100
That's my
meters
point.
thick.
Yeah,
It has to be a bit bigger than that.
or it's different things.
I think we'll find out this summer.
Yeah, that's
Yeah,
more to
questions.
preempt the Z10, but you're saying that Z10 works here even with all the power lines and.
This place is very quiet. This is just a bunch of wheat fields. So this is a nice place to work from an EM perspective. Worst thing you have to deal with is expenses. And I mean Z10. I don't think Z10 is seeing this very well. So that's there's definitely an interesting Z10 story, but I don't think Z10 by itself would have been able to characterize this really. Is that it?
Great.
Yeah.
No more questions? We still have 10 more minutes, but we can. 1 second, I have Ross. Ross says, thanks. I was just curious of the order of magnitude for this. Oh, that was a compute. He was asking about the price as a price. That's okay.
Okay. Right.
Sorry.
Do you see black shell in the recent drill, or do you have any physical property data for that?
Yeah, there's no physical property data, but definitely there's black shales, and there's just black shales everywhere. But there are black shales in the bottom of several holes. In that BSC lithology, which is kind of what you expect to see as well.
Okay, well, thanks, Scott, again.